Alright guys, welcome to this page of the notes, and let's go ahead and do a biology problem. Here's what we've got. A type of bacteria is growing exponentially according to the model, which I've given you here, y equals 1000 e to the kt, where t is the time in minutes. Alright, this is a two-part problem. Let's start with part A. Here's what I want to know in part A. If there are 1,000 cells initially and 1,650 cells after 40 minutes, I want you to find the value of K for the bacteria culture given above. All right, well, that's not that bad. Let's see what we get here. The equation I've been given is y equals 1,000 e to the kt. But here's what I know. I know I started with 1,000 cells. That's already there. I finish with 1,650, and t has to be 40 minutes. Plug all that stuff in. 1,650 is equal to 1,000 e to the k times 40. Well, here we go. I've got my equation, my formula set up. I need to solve for k. K is in the exponent position. That means I'm going to need to get it out of the exponent position. But we'll burn that in a second. First thing I need to do is divide by 1,000. If you divide 1,650 by 1,000, you get 1.65. Okay. Now, we've seen this before in a couple other problems. The k I'm trying to solve for, it's in the exponent position. I need to get it out. Since I have a base e exponential function, take the ln of both sides. If I take the ln of this side, ln and e will cancel each other out, leaving me with just the 40k. Which means k is going to be equal to the ln of 1.65 divided by 40. All right, so let's do that. You plug this stuff into your calculator, take the ln of 1.65, divide that number by 40, and here's what I get. Don't lose any of your decimal places. 0.012519 3822, right? That's what I get for the value of k if you do ln of 1.65 and then divide by 40. Now, here's the interesting thing. If we go ahead and read part B, here's what I get. Suppose a second type of bacteria is growing exponentially according to the model, so I give you a different exponential growth equation for a different bacteria culture, right? This bacteria culture is not the same as this one. This is the first one, this is the second bacteria culture, two different growth rates. I want you to determine how long it will be before the number of cells in this one, in this guy right here, before the number of cells in this bacteria culture is bigger, exceeds the number of cells in the previous bacteria culture. You see what it's saying? You've got this first culture and a second culture. And I want to know how long will it be before this bacteria culture, the population is bigger than the population in the first bacteria culture. Well, what that means is that I need the equation, the exponential growth equation for the first bacteria culture, which I can do because I now know my value of k. So here we go. I'm going to use y equals 1,000 e to the 0.0125193822 t. Again, you don't want to lose any of those decimal points, all right? Make sure you keep all those decimal points. I know it's going to be kind of a pain in the butt, but don't lose any of them. And we're going to go ahead and do part B. So let me go ahead and erase some of this so that you can easily see my work. Erase, erase, erase. Erase, 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 erase. All right, so we'll go ahead and erase all this, and that way I can just start my work for part B right here, and that way we can still see the problem and the work that I'm doing. So here we go, part B. What they want you to do, right, is set this bacteria culture greater, right, exceeds this bacteria culture is greater than this bacteria culture. Well, that's easy. 1,000 E to the 0.01251938222T is going to be less than 50 E to the 0.0432T. That's a 2. 2, 2. Okay, here we go. Now, here's what I'm going to have to do. This one's a little tricky, so just stick with me on it. What we need to do, right, is we need to solve for t. The t's, right, are in the exponent position, and I know that I'm going to have to get them out. Since I have a base e exponential function, we're going to take the ln of both sides, and that actually is going to be our first step. I'm going to take the ln right now. The ln of 1,000 times e to this whole guy up here. Let me just go ahead and for now call it 0.01. I'll come back and take that whole number in just a second. 0.01, it'll just help me save a little bit of time, is less than the ln of 50 times e to the 0.0432t. Okay, step number 2. Since I've taken the ln, right, and I'll come back, don't lose this number, I'll come back and add all those decimal points. I just don't want to write them out every time. It'll take forever to go through this problem. But here we go. ln, please notice I'm taking the ln of a product. This is the property, the exponential property of logarithms. It's the product property where I can now split these guys up using addition. It'll be the ln of 1,000 plus the ln of this exponential function. Same thing on this side. That's multiplication. I can split these guys up using addition. ln of 50 plus the ln of the exponential function. So here we go. I have the ln of 1,000 plus the ln of e to the 0.01. I promise I'll bring all those decimal places back in just a second. I just don't want to write them every time. Is less than the ln of 50 plus the ln of e to the 0.0432t. All right, let me slide up a little bit so you can see my work. Here we go. First, ln and e, inverse functions, they cancel each other out. Same thing over here. So all that's left is just the exponents. ln of 1,000 plus 0.01t less than ln of 50 plus 0.0432t. All right, here we go. Now it's time to solve for t. In order to do that, I need to get the t's on the same side. I've got a t here, I've got a t here. Please notice that this number is smaller than this number. So I'm going to subtract this t to this side, plus ln of 50 is smaller than the ln of 1,000. So I'll subtract the ln of 50 to this side, right? So here we go. I'll have the ln of 1,000 minus the ln of 50 is less than 0.0432t minus, let me go ahead and get my whole decimal back in there, 0.0125193822t. Whew. All right, here we go. The home stretch, you're practically there. Subtraction. It's the quotient property. I can put these two guys together as the ln of 1,000 divided by 50. Is less than, I have a t here and a t here. That's my GCF. Pull it out. T. And then here's what's left. 0.0432 minus 0.0125193822. Go ahead and do that subtraction. If you do that subtraction, you wind up with 0.03068 0.0617.8. I'm pretty sure that's what my calculator gives me. Double check. 0.3068. Oh, I missed a 0 in there. Scratch that. Let me get a 0 in there. I've got 680.6178. Okay, again, I know it's a lot of decimal places to keep track of, but you need to hang on to all those decimal places. It's really important. If you lose any of them, your answer is going to come out quite a bit different than mine. So anyway, here we go. And I know it seems for numbers this small, how could a couple of decimal places matter? Remember, we're converting to a logarithmic scale, and you guys should remember from previous problems, we take these enormous numbers in scientific notation and we convert them to logarithms, and you wind up with these nice, neat numbers. Well, now we're going the opposite direction, right? I got these nice, neat numbers. We're converting to these enormous decimals, and so all these decimal places can have a huge effect when converting to a logarithmic scale. So it's really important you don't lose any of the decimal places, or it'll surprise you how drastically different your answer can be by only losing a couple of decimal places. And it's because we're converting to a logarithmic scale. Anyway, here we go. Divide this to the other side. We wind up with t is greater than the ln of 1,000 divided by 50, all divided by 0.030680617.8. All right, this is a calculator problem. Don't fat finger something on your calculator, and you get 97.64. And remember, I told you up above in the previous problem, up above in the problem, that t is in minutes. So after 97.64 minutes, the population of that second bacteria culture has now exceeded the population of the original bacteria culture, which is really interesting considering that the original bacteria culture, that first one, started with 1,000 cells. The second bacteria culture only started with 50 cells. So even though this one started with more, because the growth rate for the second bacteria culture is a greater growth rate, eventually it'll catch up and exceed the population of the original bacteria culture, which has a much smaller growth rate. Great problem from biology, awesome application to bacteria cultures and growth rates in biology. Head on over to the next page of the notes and we'll take another look at population. I'll meet you guys there.